If you remember from last week, we stopped here and we look at the example, right? Where you have the metropolis Hastings algorithm, and we use the proposal, which is the normal distribution with mean theta and variance sigma square. And we have shown that this is actually a symmetric proposal, right? So when the symmetric proposal means that you can actually simplify the acceptance probability for the metropolis Hastings algorithm, right? And you can see that and after we simplify furthermore with the posterior distribution, and we can see that we have the exponential, the function, right? So you can actually do this, and we can get the algorithm to uh, accept or reject your proposal from the normal distribution. Okay, so last week actually I went through this because I realized that I missed this section, right? And so if you open the Metropolis Hastings example, which is a different file, right? You can see that we have a figure 1 to 6, right? So the figure 1 to 3 is actually when the uh, mean is theta and the variance. Okay, so if you look in the example, right here, we assume that the variance sigma square is a fixed value. Okay, so theta is a random, it's your proposal, but your sigma square, you have to, it's a fixed value, so you have to actually give a value to sigma square. Okay, so for example, in this case, we have two examples. First, when your sigma square is 1, right? So when your sigma square is 1, and the other one is when your sigma square is 0.36. Okay, in both cases, the starting point, your theta naught, which is your initial value, is equal to 1. Okay, and we're going to look at different iterations, right? So iteration, if you look back, iteration is your t. T is your number of iteration, right? T is number of iteration. So we're going to look at different iteration t values, right? Which are 9, 100, and 5,000 iterations from the Metropolis sampler. Okay, and for both cases, we have the proposal is, so we have the target, which is a normal 0, 1. Okay, so your actual value, actual distribution is normal 0, 1, but you're using Metropolis Hastings to actually, so actually you can actually propose directly, right? But for illustration, we use a normal 0, 1 as your proposal, as your target. And you use proposal from the normal with mean theta and variance sigma square. So it's 1 and 0.36. Okay, right. So if we were to open it, okay, so wait, I have to look, right? I think it's Metropolis. Okay, so if we look at the file, okay, so you have a figure 1, right? So you have figure 1 is where you have the 9 iteration. Right here, your sigma square is 1. Okay, and you can you have the figure. They are actually figure 1. There are actually a few figures in figure 1 even. All right. So the first one is the is an example. Okay. Right. So you can see, right, that the first one is the PDF. Okay, PDF meaning that is the your actual distribution, and then you have the proposal. Okay, so you can see that the difference in between the green, the blue, and the red. Okay, wait. Yeah. Okay. Right. So there is the, okay. So meaning that the proposal is the normal minus 0.2161, right? And then we have theta star is minus 1.79. Okay, so this is just a example, right, of the actual density, and then the the proposal density that you propose from the current value, and then you propose to move to a different different x actually. Okay, and the second one is actually the trace plot. Okay, trace plot meaning that the value of the theta, so meaning that this is actually your theta here, right? So the value of your theta actually move. So you start from, so here you remember your theta, your initial value, right? Your theta naught is equal to 1. Okay, your theta naught is equal to 1. So you start with, that's why you start with 1, right? And you can see that the proposal, right, your theta star is actually normal, which means theta, which is the current your theta, or you can just put, like your theta, your previous value, and then it's actually, and your sigma square equals to 1. Okay, and you can see these are the actual movement of your theta, right? Meaning that so you look at the iteration, it will be 0, initial value is 1, then you have iteration is your t, so you have t1, t2, t3, t4, t5, and so on, right? And you can see that the movement of your theta as it accept or reject the proposal. Okay, and if you look at in the table, right, you can see that actually from 0, so you start with theta 0, or sorry, theta 0 here equals to 1. So then you have this is your t, so this is actually your theta 1, theta 2, and so on. And you can see that they actually accept, and then they reject at t5, and then you have accept, and then reject at t9. Okay, and you can actually see that, right? If you have the movement here, right? You can see here that they are, if you look at this figure, right, the theta actually changes, right? And then part here, from 4 to 5, right, you can see that it's a straight line, meaning that there is no change, right? Meaning going from T4 to T5, you can see that there is no change here. That's why it's a flat line. Okay, and then again from 8 to 9. Okay, actually, if you look here, there's a very small change, right? But from 8 to 9 here also there is no change. And actually from 7 to 8 there is a change. You can see in the table. From 7 to 8 there is a change, but it's just the value of the theta star is very close, 0.251 and 0.216, right? So it's very close. So that's why in the plot it looks like it's a flat line, but it's not. Okay, so there is actually a change from 7 to 8, but it's a very small change, right? Because remember, right, when you have the sampler, which is the normal, it actually sample any value, meaning that if I were to go from 7 to 8, right, it will go actually, I will propose from my 7 is minus 0.251, right? Sigma square 1. So I will propose to move from here, and then I will propose, so this is my mean now, this is my new mean. Then I will propose to move to another value, randomly pick from normal with this mean and this variance. Okay, so in this example, they actually propose from minus 0.25, they propose minus 0.216. So this is by coincidence, it's just a random movement. Okay, so randomly they move, so because so they actually proposed to a very close move, so it's actually just random. So you can see that there is a acceptance, but the value are actually quite close, right? And then from here to here they reject so this is actually the proposed value. They want to move from minus 0.216 to minus 1779, and this move was rejected. That's why you can see in the plot, actually this is a flat line because the proposal was actually rejected. Okay, so this is when you have 9. So okay, so usually people will use more than 9, but because this is just for illustration, so you can see that the graph of the movement of the theta, and you want to see the values of the proposal and also whether the theta is accepted or rejected. Okay, so then you get this figure. Okay, so for this figure, I think this is for the 500. Sorry, 100. So this is 100 iteration, right? Okay, and we can see that they are given us the trace plot. Okay, so trace plot is again the value of your theta, right? So you can see over the value of the theta here, meaning that this is your theta t, right? This is your theta t against the iteration which is smaller. The iteration which is your iteration. Okay, so the first plot, right? You can see that okay, make it larger. All right, you can see that actually they are moving because remember, right, the target distribution is actually normal 0, 1. Okay, so this is so you will expect that if your normal 0, 1, if you have two standard deviation away, so it will be moving between 2 and minus 2, right? Okay, but of course this is only 100, right? Okay, and the second one is the density, the observed density against the target density, right? So the blue one is your target density, and the red one is your observed density. And the third one is the autocorrelation plot between the sample. As I told you before, because of the Markov chain property, the samples are not independent. Okay, so the samples are actually correlated between each other. Okay, and you can see that there is a correlation. So the SEF, right, is not very small because there is a correlation between the samples. Okay, and if you are only using 100 iteration, then the sample mean is 0.343 and the sample variance is 0.57, right? The target, it should be normal 0, 1. I mean, the true value is normal 0, 1. Okay, so this is when using 100 iteration, right? And usually for multiple testing, you have to use more than 100. Okay, and this is if you're using 5,000, right? You can see here, right? If you are using, yes.
Question. So sorry,
Yeah.
this autocorrelation plot is the correlation between successive iterations, is it? What's this autocorrelation plot?
I think it's the autocorrelation plot between should be between the samples actually. I have to check that. I think should be between, it's not the, yeah. I think I think, no, lag means, yeah, lag 1 means the successive, yeah, usually between successive samples. Because lag 1 means xt and xt plus 1, right? Lag 2 is xt and xt plus 2. So the correlation will be between the t and t plus I, usually for the autocorrelation. So this is meaning that even with lag, supposedly we have Markov chain, right? But the lag is not just 1. Yeah, so you can see that yeah, they have a behavior of sort of like the samples have more than one lag, basically. So they are testing like 1, like 2, like 3, and up to like 30 even. Between successive samples, yes. Okay.
Okay, thanks.
Okay, yeah. Anyways, for 5,000, you can see that the values are moving between the 2 minus 2 and the red. The observed density is close to the true density, which is a blue one. And yeah, and he was asking about the autocalculation. Yeah, it's still high because again, it's not a independent sample. Okay. Okay, and the mean, now you can see, right, the sample mean is 0.01 and the sample variance is 0.98, which is actually close to the true value of normal 0.1. Okay, so the thing here is because we have to choose the sigma square, right? So here in the figure 1 to 3, we are actually looking at the sigma, which is sigma square equals to 1. Okay, which is the variance is actually 1. Okay, so the other option is actually we can change the variance sigma square to a different value. So for example, we change it to sigma square, which is 0.36, right? And you can see over here that you have the values is you still have the same initial value, which is 1, and then they actually moving, either they accept or reject. So, but this is still 2 out of 10, 9 are rejected. So similar to before. Okay. But so but with 9 iteration, we cannot really see much. But if we look at here, right, so this is actually 101. Again, we can see, right, they are moving between 2 and minus 2, but still 100. Again, it's not really a good sample, a good number of sample actually. Okay, but if we look at 5,000, right, you can see that there actually more movement. Okay, and or does it say what is the acceptance probability? Oh, okay, it doesn't actually. All right. Okay. Okay, so the aim here, right? Okay, if you look at the last line here, right? So if we compare this with figure 3, right, meaning that the other figure when your sigma square equals to 1, right? So if we have your sigma square is smaller, meaning that our proposal will have a smaller jumps because the variance is smaller actually. Okay, but so this will actually increase your acceptance rate. Okay, which is your alpha will be increased, but we will actually reduce your mixing. Okay, we reduce mixing. Okay, what does it mean, right? Reduce mixing means that the movement is actually smaller. Okay, okay, maybe I have to show this one, right? So you can see, right, if I have 100, this is sigma square 0.36. You can see they are actually moving more, but the distance between the movement is smaller. Okay, because the variance is, okay, let me just say, right, if you have your proposal, right, is normal with variance is 0.36, right, meaning that your because it's normal, right, then your proposal actually is going to be, right, if you're normal, right, it will be like, for example, is we have the mean at theta, and then it can move like 2 standard deviation, right? 2 times 0.36, which is, I guess, 0.6. 0.6, so it's around 1.2. So this is if you have a sigma square is 0.36. But if you have a larger, sigma, right, which is from figure 3, your sigma square is 1. Okay, then you have like theta plus minus 2. Okay, so this means that if I were to have a proposal, right, then I can actually move, my movement is actually maximum around 1.2, right? But if I have a sigma square 1, then I can actually move 2. So my jumps, meaning that if I'm here, right, I can go higher or go lower. I mean, there is a probability of moving higher or lower, right? But if my sigma, if my difference here is small, then it's more like, you know, you are proposing smaller or shorter proposals. You know, it's like more like, it's shorter means it's close, like it's not very high. Maybe like this. But if you have like 2, then means that you can go higher, then it will go like mixing. So the distance, the probability of the distance is actually higher. Okay, so this is my mixing. So here the chance, right? The chance of, if you have a smaller variance, the chance of the movement of your proposal is actually shorter or lower than if you have a higher variance. Okay, so you can see, for example, right, if this is your, this is from this is actually when your sigma square is 0.36, right? And if you compare to the one when your, right, you can see over here, if your sigma here, your sigma here is 1, right? You can see that, right? The length, right? The movement of the theta actually can be higher. Higher means you can go up very high or you can go down very high. Okay, this is because your proposal have a higher variance, so they have a higher chance. They can also have a higher chance to move more, or more means like longer distance. Okay, so if you compare to the one with sigma square, which is 0.36, right? You can see that the jumps is not as high as the one as from before. Okay, because we already limited, as I say, right? The maximum, or because if you look at sigma square normal, right? I mean, mostly they will go like 2 standard deviation, so 1.2. So for example, they might go from 1 to minus 1. Oh, sorry, minus 1 to 1. So that's maximum, right? Okay. Or but if you have a variance is higher, then you might go from minus 1 to 2, right? So the jumps is, they have a possibility of higher jumps. Okay, so this actually means that the mixing is more, because you can actually move around the support more. Okay, but the drawback is, okay, if you remember the proposal, right? Because if we propose, if the jump is too high, sometimes we reject more. Okay, because for example, right, for example, right, if I change to maybe, right, so maybe if I'm here, right, and I propose a higher jump, too much high, so this one will be rejected, right? Or if I'm down here, maybe down here, and then I want to propose go to down here, got rejected. Okay, so the sigma square, if you have a sigma square which is large, it can't be too large, because if it's too large, then you might propose a value which is outside of the range, right? So if you propose too much of the value which is outside the range, then it will get rejected more. So then your alpha, your assessment probability will be low. Okay, so when you choose your sigma square, you have to find the balance between sigma which is not too small but not too large. Okay, that is usually we have to use by trial and error, because because this is because we know the answer, right? But in the real application, we don't really know what is the true value of the sigma square. You have to guess, or try and error, try to see whether it's good or not. That's the only way with multiple testing actually. Okay, right. So that is the comment for this. Okay, so going back to the lecture. Okay, so then we're going to look at the next method, which is the git sampler. Okay, so what happened with the git sampler is we are actually using, so git sampler is actually a subset or a special case of the multiple testing. Okay, so if we have a p dimension, meaning that we have theta is a theta 1 to theta p, so we want to sample from your theta with p parameters, which is theta 1 to theta p. Okay, so we have a starting point at 0. Okay, so what is the notation here is actually for the git sampler, this is actually a special case of multiple setting where each iteration, so this is the important part, right? Each iteration T consists of P multiple testing step with representative probability 1. Okay, meaning that each step of the multiple testing is always accepted. Okay, and the proposal, the proposal or the distribution that we sample from is actually the conditional distribution. So for example, we have theta 1, we sample from the conditional of distribution of theta 1 given the rest of the parameters. Okay, but at iteration T, right? So okay, so this is where you have to order it, right? Theta 1, so the ordering is theta 1, theta 2 until theta P, right? So we assuming we update theta 1 first, and then we update theta 2, and then we update theta 3 up to theta P. Okay, so means that at time T, if we update theta 1 first, right, theta 2, theta 3, theta 4, up to theta P are not updated yet. Okay, so because this is, it's called single case, single step, I can't remember, single step multiple testing, right? Meaning that we actually update one parameter at a time, okay? And but when we update theta 1, theta 2, and up to theta P, they are not updated yet, okay? So the next one is when we update theta, the next theta I, for example, theta I, theta 2, right? So if you update theta 2, theta 1 already updated, then we update theta 2, but theta 3, theta 4 up to theta P are not updated yet. Okay, so meaning that if I update theta I, right, theta 1 to theta I minus 1 have been updated, but I plus 1 to I plus 1 to P are not updated yet. Okay, so this means that I will update the parameter one by one. Okay, and for each of the parameter theta I will update from the conditional distribution. Okay, and for the git sampling, this means that the conditional distribution is a known distribution. So when we find the conditional distribution of the parameter theta I, it's actually a known distribution. So we can just use the distribution as it is. Okay, this is why it says that it's like multiple testing with a certain probability of 1. Okay, and it can be shown mean that if you were to use it means that if you remember your alpha, right? Your alpha for the multiple testing is actually mean we have 1, and then we have your posterior, right? So posterior, and then you have your Q, right? Theta 1 given theta star. Then you have your P theta Y Q. So theta, so this is T minus 1. Well, T minus 1. Okay, I think the notation you have to be careful. Here I just put, because the problem is we have theta P, right? So I just use the subscript as the parameter and the bracket as the time. Okay, because if not, you get confused. Theta star theta T minus 1. Okay. Okay, so if my handwriting. Yeah. Okay, maybe I have to write. It's not space actually, not space. Okay, maybe I have to just write the part. If you look at that, this what I call it, this ratio, yes, right? If you put t minus 1, okay, I just put the top one, right? So if you look at this ratio from the metropolis testing, right? If you put in your proposal, okay, so if you want to have your metropolis testing, then your proposal is actually the conditional distribution. So this is actually, if you put this in here, right? Okay, and your posterior is actually conditional. It's actually also this one multiplied by the rest. So you can actually show that this alpha, if this is alpha, right? Alpha is the mean of this function one, and the one at the bottom, right? P and Q. So you can actually show that this will actually what call it? This will actually simplify to 1. Okay, right? I mean, we can show part. Maybe I put it as an exercise. So anyway, so this means that the gate sampler is actually a special case of the metropolis testing, where your alpha is actually equal to 1. So it means that all the proposals are actually accepted. Okay, but the parameters are actually updated one by one. Okay, not at the same time. So this means that each of the theta I have different distribution, conditional distribution, or different proposal, and all the proposals are accepted. So it means they will change, right? They will be accepted. Okay, right. Okay, so now suppose we have an example now, right? So we have y is normal with mean theta and variance phi, and then we have the prior is 1 over phi, and then this is the posterior that we get from before. So actually this is from the previous example from last chapter, right? And how do we actually get the how do we actually use the gate sampler to generate from this posterior distribution? Okay, so how do we do this is actually, first we have to find the conditional, the conditional posterior for each parameter. Okay, so what is the conditional posterior? So because here we have two parameters, which is theta and phi, so we're going to have two conditional posterior. First is the first conditional distribution is actually your theta. Okay, so if you have conditional, means theta given your parameter and given your data. Okay, so and then the other one is theta phi. All right, so the other one should be your phi given your theta and your data. Okay, so meaning that you have to find the conditional distribution of each parameter given the rest. The rest means the other parameters and also the data. Okay, so if you look at the conditional distribution of theta given phi and y, okay, so if you use the posterior, right, which is from here, so by definition, this is actually your posterior, right? Your joint posterior divided by the marginal posterior, right, or phi. Okay, but because we have the conditional posterior given phi, so here we assume that the phi here is a constant. So the marginal posterior of phi is also a constant. So this is actually just a proportional of your joint posterior, right? Meaning that you don't have to find the marginal posterior for phi, because that is just phi now is just a constant. So we can just play around with the joint posterior. Okay, and so if you look at our joint posterior, so again now this is the Bayesian trick, right? You assume that your theta is your parameter and your phi and y is a known or is constant. So you only left with theta, right? So we only have the phi here is constant, so you can get rid of it. Okay, and so we only have the n, right? N over 2 phi y bar minus theta square. Okay, so here means that because phi, we assume for this case, for this conditional posterior, your phi now is a constant. So we get rid of it, right? Because it's also exponential also. The S is only the data. There's no theta inside your S. So again, we get rid of it. So we only left with this. Okay. And if you look over here, so again, this is the Bayesian scale. This is a kernel of a normal. Okay, this is a kernel of normal, right? And to make it easier to see, you just change this to theta minus y bar, right? This square thing is theta minus y bar. So this is actually a normal kernel, right? So theta given phi and y is normal. So you can see this is a normal kernel. So theta is your parameter now. So y bar here is your mean, and your variance is phi over n. Okay, so you have to recognize that this is a kernel of a normal with what mean and what variance. Okay, so that is so now the conditional posterior of theta now is a normal. Okay, then you have the phi given theta and y. Okay, so this is, so if you look over there, okay, so if you look at the joint posterior, right, actually all of those have a phi, right? So actually phi is the whole thing. Phi is this one. Okay, but if you put here plus 1, then you have exponential, or no, s plus n minus theta square over 2. Okay, so if you look at this, then you should recognize that this is the kernel of inverse gamma. Okay, so phi given theta and y actually is a inverse gamma, right? So this is minus alpha plus 1, right? So your alpha is n over 2, and your beta is minus 1 over phi times your beta. So this whole thing is your beta. Okay, so then they have a normal inverse gamma and normal distribution, conditional distribution. Okay, so you can see over here, right? If since we assume that for theta, if you find the theta given phi is a constant, so you can see that in the joint conditional, your theta can also depend on your phi. Okay, your phi here inside here, inside the conditional posterior, it as if your phi is a constant, and if you have your phi given theta, it is as if your theta here is a constant also for phi. Okay, so when you do the Gibbs sampler, right, of course, first you have to choose your initial value. Okay, so you can choose your initial value, Okay, right. And then when you do your iteration, when you update your iteration T, okay, so you have to generate or choose, right? Generate, maybe generate your theta T. Okay, so at each iteration T means that you will start, right? So when you add iteration T, you will start here. Currently, you have your previous value, which is your theta T minus 1, and you have your phi theta, phi T minus 1. So you start it here. So at iteration T, you have this is your current value. So when you update your theta T, then your phi is not yet updated. Okay, this means that if I were to use a value of your phi, then your phi is still not updated. So it's phi T minus 1. Okay, and then after I update my theta, then I update my phi, right? And then this will be my inverse gamma. Then because I already update my theta T, so this means that I actually use values of theta which is already updated. So it's n pi bar minus theta T here. Okay, and then 3 I just repeat for my iteration. Okay, so this means that when you writing the ordering, right? So the ordering matters, right? So if you put theta and phi, means you want to update your theta first and then you update your phi first. Then that means when you first update your theta at time t, then your phi is not yet updated. Okay, so this means that your theta t, your proposal of your theta t will depend on your phi t minus 1. Okay, but after that, after you update your theta, then you want to update your phi, right? So at this time, your theta is already updated. Okay, so you have to use theta t. Okay, so just please be aware of that when you're doing gate sampling, that the ordering matters, which one you update first. Okay, so if you have, this is only, you have 2, right? If you have more than 2, then it will be 1, 2, 3. Okay, so then it will be 1, update 1 first, and then 2 first, and then 3 first. So this means if you update 1, 2 and 3 have not been updated yet. So you have to, this is you have to update, it's called, I think it's called a single component multiple testing. Right, single component testing means you update component by component. So if you update the first component, the second, third, and so on, component is not yet updated. Okay, so then you update one by one, and then so one by one in turn, right? In turn, so if you do this gate sampling, means that you get a sample. So the sample that you will get is actually theta 1, phi 1, right? Theta 2, phi 2, up to, for example, if you do n iteration, then theta t phi, theta n phi n. So these are the samples. It's actually, you have like a pad samples of time 1 up to time n. Then you have your phi 1, theta 1 phi 1, theta 2 phi 2, and up to theta n phi n. Okay, then you have a sample of n for the parameters, which is a theta and phi. Right. So again, for this gate sampling means that you need your Bayesian skill, right? Meaning that you have to find the you have to simplify it, and then look at the kernel, and then you have to identify the distribution. Okay. Right. Okay.
Sorry.
Yes.
Question. So, will our estimates be sensitive to the order that we update the parameter?
I think it might be actually. Depends on the parameter. Okay, but that's why you need to that's why you need to have a more like a big sample. Okay, to make sure they are mixing well actually. Because if you have if your iteration is large, then you will hope. I mean, your hope is actually right that after they have converged, then the sample will be okay. Okay, but in practice, yes, actually, I do find it when we do it right. Sometimes the ordering of, because here, okay, for this case, right, because this is actually the mean and the variance, right? Okay, and usually, I don't know, is it by default or by practice or whatever, usually people will update the mean first, then they will update the variance. So I don't know, that's like a rule of thumb lah. Maybe it's just like it's just what call it, a behavior or say a preference. Okay, but supposedly it doesn't matter in the long run, right? But in the short run, yeah, sometimes it does actually. Okay. So yeah, the other way is you can also play around and change the order to see whether it's affected or not. But in theory, supposedly if you do it for a long time, long time is a large number of iterations, then after convergence, then it shouldn't matter.
Okay. Understand.
Okay. Yeah, but in practice, yeah, sometimes it does actually. Okay.
Hello. Yeah.
So for
Sorry.
this, yeah.
Yeah, quick one. So basically, we use Gibbs sampler for when our posterior is multivariable, is it?
Yes.
It's
yeah, because if you have only one parameter, okay, so if you have only one parameter, what you're doing is basically Gibbs sampler, right? Because you are sampling from the posterior, right? And because you know already the posterior, so as long as you can identify the posterior, like our example from chapter 1 and 2, right? Or 3, we know already the distribution, right? So basically that is already the Gibbs sampler because you already know the distribution. But if you don't know the distribution, it's an unknown distribution, then even with one univariate, you can still do multiplicity testing. So the Gibbs sampler is only if this one example, Gibbs sampler because we can actually identify, right? Identify this is like normal, this is inverse gamma. So we use the conditional distribution which is known. So we just directly use the distribution itself. So that is the aim of the Gibbs sampler, right? Because if you use the distribution itself by itself, we can use it directly, right? So it means that the acceptance is 1 because we sample and we accept, right? Okay, but so usually you do it, and this is for multivariate, also multi-dimensional case. For one dimension, the one that we do in chapter 1, chapter 2 and 3, the one that when we recognize the distribution, right? So this already using the distribution itself directly. So we don't need the MH or we don't need the Gibbs sampler because we already know the distribution. Yeah. So in this case,
okay.
yeah. Okay. So in this case,
so you're saying,
yeah.
Sorry.
Yes.
Yeah. So you're saying that when we can like get out these conditional probabilities that are recognizable, then we use the Gibbs sampler lah. It's easier because we can recognize the form straight away. So
yeah,
we can sample straight away.
Yeah. So the other example when we use the normal 0, 1 from the MH, that one is because that one is because is a illustration. So right, you don't really need MH, right? We don't really need MH to do it, but the one is just to show you. So okay, so why do we need this? Is because if you look at this join PDF, right? Join posterior here, this one, right? You cannot use it directly, right? Because here, even though it's called inverse gamma inverse normal gamma, whatever, right, the name of distribution, but we cannot actually sample from it directly. Okay, so the only way to do it is to use multiple testing. And in this case, the multiple testing can be reduced to gate sampler because the conditional is known. But
Okay,
you can
understand.
also, yeah. So you can also actually, but okay, it doesn't mean that when you use a gate sampler, you have to use gate sampler because the MH, right, you can mix, right? For example, right, if I find theta is known, I use a gate sampler. Maybe I look at the phi. Maybe in this case, the phi, right, is unknown. So I can also use MH. So I can also use a mixture of MH, gate sampler, and other things. So you can actually use a MH, a different version. I mean, one sample, if you have like P dimension, right? Sorry, P parameters, you can actually use a mixture of different MH methods, not only one actually. So this one you use MH, this one you use and the wall, this one you use gate sampler, can, right? So you can actually use a mixture, yeah. Okay.
Okay, yeah, understand. Thank you. Thank you very much.
Right. Yeah, but but yeah, usually it's for multi-dimension, for more than one parameter.
So the underlying step for the difference between the skips and the metropolis testing is that metropolis testing, we rely on this proposal distribution, whereas
Yes.
skips, because we are able to identify
we use it
the
directly.
conditional distribution of the parameters, then we just sample directly from there. That's the main difference in the approach, is it?
Yes. Yeah. So and the gate sampler we always accept because we propose is from this its own distribution, right? So we never reject the gate sampler. There's no alpha. There's no acceptance rejection. It's a acceptance with probability 1. But for the MH, yes, we propose we can accept or we can reject. And because we have to choose the proposal distribution for the MH. Okay.
Last thing to clarify is that we can use metropolis testing for multi-parameter also.
Can.
Yes.
Okay. Yes.
Yeah.
Right. Yeah. Yeah. Because the example I give you is the simpler one. Yes, but you can use it, right? So maybe go back, right? So if meaning, for example, right, if like theta, I use MH, right, and phi I use MH, can. I mean, in this case we don't have to, but if the conditional posterior is not a non-distribution, then I can use MH for theta and I can use MH for phi. So it's actually called a single component multiple testing. So meaning I can use MH for theta and phi separately. So I have a proposal for theta and I have a proposal for phi. Okay. Or there are also other ways is you can actually propose theta and phi together. I mean, you can propose the value of theta and phi together. Also can. Yeah. So there's actually a variety of ways actually.
Okay.
Okay. Okay. All right. So okay. So going back to this one. Oh, sorry. This one is a different. This one is a different example. Okay, so here, right here, okay, so this one you can try on your own because actually we don't have much time. So this one you can try on your own to find, but both are actually you can find the conditional posterior for theta 1 and theta 2. So theta 1 is actually binomial and theta 2, and then I mean theta 2 given theta 1 is actually beta, right? And theta 1 plus alpha and minus theta 1 plus beta. Actually, you can have a look, right? Okay, so here when you do this looking at the kernel and whatever, so the important part here is to look at whether the theta, whether the parameter is discrete or continuous. Okay, so the important part here is theta 1 is from 0, 1, 2, and it's a discrete. And theta 2 is between 0 and 1. Right, so this is given here. Okay, so meaning that your theta 1 is discrete, so you must have a discrete distribution. And theta 2 is between 0 and 1. So the only thing that theta 2 can be is like either beta or uniform, right? Okay, so you can see, so the theta 1 can be binomial, Poisson, whatever. Okay, but if you just look at your conditional posterior, right, you can see that here, this is your theta 1. The one here, and this is theta 1, and this is theta 1 there, right? So this is actually, if you rearrange and get rid of the other things, that this is, it will have a binomial kernel, right? And if you look at theta 2, so theta 2 is, this is theta 2 and theta 2, right? So again, this is a beta kernel, right? So you can show, right? You can do this as a practice. You can show that your theta 1 is binomial and theta 2, the conditional of theta 1 is binomial and the conditional of theta 2 is a beta, right? So then if you were to use, find the gate sampler, okay, so again, we have our initial value, which is, this is where, I use theta 1 and theta 2. So this is at time 0. So you have our initial value. And then we iteration t, right? So we have, we generate our theta 1 at time t, right? So it depends on theta 2 t minus 1. Okay, so then it will be binomial and theta 2 t minus 1. Right? Okay, and you have your theta 2 at times t, but then your theta 1 is already updated, so theta 1 is t. So this is actually a beta with theta 1 t plus alpha, and we have n minus theta 1 t plus beta. Okay, right? So here, so this is just like example to show, right? You can have also a mixture of discrete and continuous, right? So, but you have to recognize whether it's a discrete or continuous distribution. Okay, and then when you update, then again you have to be careful. Yeah, as you said before, right? Okay, which one do you update? Is it the beta? Is it theta 1 and theta 2? So actually, in theory, it doesn't matter. Okay, so for example, you update theta 1, then you update theta 2, then you have to follow the ordering, which one is already updated, which one haven't not yet been updated, and then you have to update according to the order. Okay, as long as you put it the order, then you just update it according to the order that you have chosen. So in this case, we update theta 1 first, well, because the name is theta 1, theta 2, right? So usually you follow the name, theta 1 first and then theta 2. Okay, so then, because this is actually following the other PDF file that I've uploaded, which is a gives.pdf, right? So then we're looking at the values of n, 50, and 1500. And then we are looking at different values of your alpha, alpha and beta. Okay, alpha and beta actually is the, if you look over here, alpha and beta is actually the constant here, the constant for inside the beta part. Okay, or it could also be from the prior. So it might be it might also affect your simulation. Okay, so here, so here instead of theta, they're using x, so we have x1 and x2. right? So then x1 is actually your theta 1 and x2 is your theta 2. Okay, and then you can see that that they are looking. So here you can see, right? If you're looking at 50 iterations for x1, which is theta 1, x1 and x2, then you can see that the values of x1 is discrete because it's binomial, and the values of x2, which is beta, is between 0 and 1. Okay, right? So then, and if you look at the histogram, right, then you can actually see sort of the marginal distribution for your x1 and x2, sort of. Okay, right. So this is for 50 iterations, right? But if we use this is what? This is 1,500. Sorry. So this is 1,500, right? So you can see the movement here. Okay, so the movement here, but you can also see, right, the mixing, meaning that they are moving because this is like they're still not independent because no, your x1 depends on x2. So what I mean was because, so even though they are using the conditional posterior, but remember, right, when you update, it's actually x, maybe I put x1, right? You have x1 and you have x2, right, at time 0. So this is your initial value. Then you have your x1 and x2 at time 1. Sorry, at time 1. Okay. So but the thing here is x1 at time 1 will depend on x2, right? And x2 at time 1 will depend on x1, like this. Okay, and then you have your x1 and x2 at time 2, right? Time 2. Then this will depend on your x2 here and this one. Okay, so you can see, right, they are actually not independent, and they actually depends on the previous value a lot. A lot means they have like a history, right? So you can see that the dependency here, x1 depends on x2, but x2 depends on x1. So they actually depends on the previous iteration, but they also depends on the ordering, and they also depends on how many iterations that you have. Okay, that's why, right, if you look over here, if you plot your x1 and x2 against each other, you can see that they are actually sort of the movement of x1 and x2 actually connected to each other because of the dependency, right? Because of this dependency of your x1 and x2 to the previous value. Okay, so you can see the plot here. Okay, and because of that also, then you can see that the mixing, right, of the values for your x1 and x2 sometimes also quite close to each other, right? Because as I say, they are not independent sample. Okay, right? And if you were to look at the marginal, then it should be supposedly a straight line, uniform 0, 1. Okay, the marginal, right? And after 1,500, then sort of uniform. Okay, and so this is if when your alpha and beta are equal to 1. Okay, and if you have your alpha and beta equal to alpha equals to 2 and beta equals to 3. Okay, and so you can see here that the marginal is actually a beta binomial and beta. So you have a curve here, right? So for 50 iterations, then if you have 1,500, then the histogram actually follow the curve, right? And you can see again the behavior. So this is actually because alpha and beta is different. So actually, I think based on your prior, so alpha and beta would be the distribution from your prior. Okay, so this is just for illustration. Right. Okay. Right. Okay, so this is okay, so then for the final part is we're going to look about this is what I say by convergence and efficiency, right? Because the metropolis Hastings produced a Markov chain, right? But it needs some assumption for convergence, which is it must have a unique stationary distribution, right? And the minimal liquidity conditions are required, right? So that our target distribution is indeed the our stationary distribution is indeed the target distribution which is the posterior. Okay, so again, as you use the metropolis testing, it depends on a good choice of your proposal Q. Okay, so in practice, we want a high acceptance probability. So acceptance is your alpha, right? We want a high alpha. So if you use a good proposal Q, which is close to your posterior, then it will be a good proposal distribution. Okay, but on the other hand, we want to explore the whole distribution, right? Meaning that we want to move around your theta, and we don't want to have if your variance is too small, then you're moving very very small, then you will not cover a lot of the support of your theta. Okay, and this means that the chain does not move around very quickly, and this is called a slow mixing. Okay, so if you remember the picture that I shared with you before, if you say is a slow mixing, right? Meaning that, for example, we have the graph, right? And then the values are actually, it's called sticking to each other, it's moving a lot, but it's moving very close to each other like this, like this, right? And so this is called a slow mixing actually. Okay, so meaning that it's moving around, but the values they are moving. The steps of the proposal are actually very quite small, and they are actually the proposals are actually close to the current value. So they are moving, but they are sort of sticking to each other, and this is actually called a slope mixing. Okay, right. So the one thing about the gate sampler is of course we don't have to worry about the alpha, because the gate sampler has a probability has the acceptance of 1. Okay, but as I said, as from the graph that I showed you before, right? If the parameters are highly correlated, then we might experience the slope mixing, like the picture that I've shown you before. Okay, so ideally, in theory, we want the parameters to be as close to independent as possible. Okay, but of course, in practical, this might not be happening. Okay, so how do we want to improve our gate sampler? For example, we can use a transformation, right? If you use p theta, then maybe we can use p phi instead. So they might be an advantage if you use transformation on our parameters. Okay. So what will happen, right, after we get our sample from our MH or gate sampler? Okay, so as I said before, if we sample for a long time, in theory, the sample will come from the target, which is our posterior. Okay, so since we want the sample after the convergence, right? So we will actually have to discard. Discard means we have to throw away the values before the convergence. Okay, and this is actually called the burn-in. Right, this is called the burn-in, right? And the length of the burn-in depends on the rate of convergence and how close is your true posterior, the sample to the true posterior. Okay, so but in practice, right, what is the rate of convergence? How long is the burn-in, right? It's actually in practical, it's actually difficult to estimate actually. Right, so maybe you can actually look at the time series plot, right? So you can see the mixing, like as I said before, if you see the problem like this graph, right, they are sticking to each other. So this will actually indicate slope mixing. Okay, so this means that maybe you need more iterations, right? A higher number of iterations to see whether it will improve or not. Okay, so this one way is you use that time series plot to see whether your MCMC has converged or not. Okay, the other one is actually maybe to improve, you can actually run multiple chains from different starting points. Meaning that if you have your theta naught, your starting point, you can actually change your theta naught to different values to see whether the values actually converge to the same point or not. Okay, so you use a different theta naught and you see the convergence of the different chains. Okay, so that is also one way to see to check whether the convergence has happened or not. Okay, so if the Markov chain is ergodic, right? After we throw away the burn-in, for example, we have M burn-in, right? M burn-in, then the leftover sample, which is N minus M, we will assume that that come from our target distribution, which is the posterior. So we can use for example, we can use the average, right, to find the expectation of the function f. Okay, which according to the theory can estimate the expectation of your f. Okay, by theory. Okay, we can also use it like what we did in chapter 3. We can find the mode, percentile, probabilities, right? So we can actually use the sample. So instead of using the theory, we can use the what they call it? We can use the empirical. Yeah, so this you can use the empirical value or empirical mode or from the empirical percentile or using the empirical property. Okay, so you can actually use the sample to estimate the values that you want using by empirical method, right? By using summation, like estimation. Okay. For example, you might find the mean, right? If you find the mean, then it will be just the summation of your theta 1. Okay, so you find the average of your theta 1 over the sample size, and that will estimate the expected value of your theta 1. Okay, and if you use transformation, right, you can also transform the sample, the value of the chain, right, to get a sample from the phi, for example, right? If you transform theta, you can use theta, the sample from theta to and transform it into the sample from phi. Okay, so question, right? So in practice, how long is long, right? You say that in theory it actually converges after a long run, after a long while, after a long iteration. But how long is long? Okay, but this is actually very complicated because it depends on your problem. Okay, because again, it's a dependent sample, right? So it depends on your posterior. If you use MH, it will depend on your proposal. Is it a good proposal or not? So everything is complicated and try and error actually. Okay. So for example, if it has a slow mixing, right, you might need more iteration, very high iteration, or maybe you need transformation, right? So there are actually formal methods which I'm not covering here in our lecture, right? But informal method, right? For example, you can try multiple values of your iteration, and you can compare your estimate, right? If they don't agree, then you have to use more. Okay, so that I think yeah, sorry, time. Okay, so the end part here is quite theoretical, right? But I think the aim here is actually after we get the sample, right, we can actually use it like empirically, right? And you can get estimate by finding the average of it, right? Or you can find the percentile or probabilities based on the sample. Okay, but usually what happen, after you get the sample, that is the easy part. The harder part is actually to get a good sample, right? So how long is how long is the duration? How much should you burn in? That is complicated because it depends on the problem. Okay, right. So any question before we stop our lecture for today, class? Anything you want to ask?
So the the early values which are discarded refers
Yes.
to the one that we rejected from the metropolitan testing, is it?
No, it's not. It's still accepted. Okay, so all right, maybe burn in, what happened here is I have to draw. So burn in is actually the one we still accept, meaning that if you have your xt, right? So this is your accepted value, right? Your t. So you have your some values here. For example, you start from here and then you still some movement, whatever, right? So and then after a while, sort of, they converge something like that. So this means this is actually the accepted value from 0. So you just choose some value in the early part here. So this is burn in M, for example. So this one you just throw away. You don't use. So it's
For
not
the
the
inference purposes lah.
the initial, the first part lah. You can say, you can think of it as the earlier part of the sample. So the earlier part of sample, because if you use macro chain, we assume that the sample will converge. But in the earlier part, maybe it has not converged yet. Okay, so we think that after some time it will converge. After M iteration it will converge. Then before the M iteration we don't use. We throw away. Then we only use after the M iteration. So that's why it's always minus M here. Minus M here, meaning that the first M we throw away, then we just use from M plus 1 to N. Okay, so this is not the rejected. This is actually from the accepted value of the MH.
Can you get a case where maybe you start on some random initial values and then it converges, but then when you try like another random initial value, it fails to converge? Is there such a case, or like, or will it always converge? If you find that one set converges, then pretty much all the other sets will converge.
Okay, there is a case like that if you have a local maximum. Okay, local maximum means that if you have multi-model, so if in practice you might have your distribution which has more than one mode, right? More than one mode, right? So for example, right, you have multi-model, for example, right? You have bivariate, you have normal, so mixture of normal, for example, right? You have mixture of normal, right? Like this, for example. This is your PDF, PDF. Okay, so could be that if you start from here, so if, for example, this is 1 and 2, right? Maybe that if you start from 1, it just move around here, right? And you start from 2, it just move around here, meaning that it cannot propose the other values. So you can actually get something called a case of you trapped in the local mode or trapped in the local maximum. So that can happen. So that's why the one, it will depend on your proposal queue. Okay, so if you have a good queue, then you can actually move from here to here, right? In theory. Okay, in practice, because you don't know, right? You don't know. That's why you queue. Sometimes you have to change. You have to try a lot of queues, right? Or variants of queues or whatever, to make sure that actually your sample is, as you say, is the correct sample. I mean, convergence lah. It's already converged. So there is actually, in practice, there is a chance that you might, that's why it's so good to try from different initial value, because it might be that your proposal is not good enough to actually move between the support. So the support here, for example, is from 0 to 3, for example, right? So maybe from 0 to 1.5, it cannot move to 2 or whatever, right? By chance. So they could be that it will be trapped in the local maximum, and then the proposal does not propose to the different to the other mode. maybe. Okay, so there is a case like that actually. Does that
Yeah,
answer your question?
even if I select even if I sample from a distribution that covers the support of the two modes like that, it can still happen. Is it?
Okay, this one is because it's a univariate, right? So you can actually look, you can actually see it.
Yeah.
The problem is in the multivariate you cannot, right? So how do you know your proposal actually cover or not? This one because you can see, right? I see this is a bimodal. So of course you know like it's a bimodal. Of course you can actually propose a good proposal, right? But in the multivariate case, you cannot see this. This is just for illustration, right? But multimodal you cannot see, right? So
Yeah.
then you think, oh, I think this is my sample already. But then if you change something, then why is my sample only around 5? Then if I do around 6, that means it's something happening in your sampler actually. Yeah.
But you should be able to know the supports, even if it's multivariate. You should know the supports of your posterior distribution.
Well, yeah. I mean, in theory, right? But then because when you have convergence, right? Convergence means actually the values is is converged to a certain value, sort of. Okay, and then because sometimes when you have like high correlation, right? Sometimes the values look a bit strange. So even though you know the support, but sometimes when you do something, yeah, right. For example, like this one, right? I mean, even like this, right? You might get like 1.5 around here, but actually, there's something going on. Because even though you know the support, but the values might not go there. Yeah, so when you're doing it in practice, it's sort of try and error lah, as you say. Yeah, you might think it's that, but it becomes something else. Sometimes.
Yeah. Okay. And like just